Today, I want to talk about a situation where when we are given some set X, we may want to say that certain elements are behaving in a similar way, and we want to provide a theory to identify those elements. So, for example, I can view these three elements as behaving the same way. I want to view some other elements as behaving in a separate way, but each of those behave the same. And once I divide the set X into these classes, I will then want to consider the set of these classes. And we will use the notion of equivalence relations. Next lecture, where we will talk about modular arithmetic. So definition. I define a relation R on a set X as a subset of the direct product of X with itself, Cartesian product of X with itself. We read X comma Y in R as X is related to Y, and I will usually write it as a tilde, like this. This relation R is an equivalence relation if it satisfies some axioms. First, we want it to be reflexive. Which means that every element is related to itself. We want R to be symmetric. Which means that if X is equivalent to Y, then, or if X is related to Y, then Y is related to X. And lastly, I want this relation to be transitive. Namely, if X is related to Y and Y is related to Z, then X is related to Z. And you may have noticed that I said that X and Y are equivalent if they're related by an equivalence relation. So if they're related with respect to an equivalence relation, we will say that X and Y are equivalent or lie in the same equivalence class. Let me first consider some examples. First, if X is a non-empty set, and I consider the relation R to be the equality. Namely, I only consider x comma x as the pairs for every x in x capital. And we can check that this is an equivalence relation because it is reflexive. So x comma x is in there for every x. It is symmetric because if x is equivalent to y, by this definition, it means that y is equal to x, and so y is also equivalent to x. And it is, of course, transitive. Now, let's consider the set X of people which live in the same village or town. Then I can say that the relation that I take is x comma y when x and y are of the same age. And we can again check that for every x, x is equivalent to x because every person has the same age as themselves. If x is the same age as y, then y is the same age as x. So the second axiom is also satisfied. And finally, if x and y are the same age and y and z are same age, it means that x and z are same age. In the same example where XR is the set of people who live in the same village, let me consider a different R is the set of pairs x comma y, where x is an ancestor of y. You can see that even reflexivity already breaks because you cannot be your own ancestor. So this relation is not reflexive. Moreover, it is not symmetric. But it is transitive because if x appears in the genealogy of y and y appears in the genealogy of z, then x will also appear in the genealogy of z. So it is transitive. But it is not an equivalence relation. And again, let's consider blood relations in the same village. Let's say that we say that x and y are related if they share a parent. you can notice that in this case, the relation is reflexive. Because you share a parent, in fact, both parents with yourself. It is symmetric. If you have a sister, then with whom you share a parent, then your sister also shares a parent with you. And let's see if it is transitive. And in this situation, it is not necessarily transitive. Because it may happen that X may share just one parent with Y, let's say a father, but Y shares another parent with Z. And in this picture, I am only considering biological parents. And we see that X and Z do not share any parent. So this is a situation exactly opposite to the third example. And it is still not an equivalence relation. However, in a small enough village, if this situation doesn't happen, then it can happen that this R defines an equivalence relation. Now let's say that we have a set X with an equivalence relation R. Then we want to observe that on this set, we have this sort of partition into cells where each cell consists of elements that are equivalent to each other. So in what sense do we want this to be a partition? A partition, not related to the fixed equivalence relation, is a collection of non-empty subsets of X such that every element of X belongs to exactly one of these subsets in the partition. I want to call these subsets cells. Cells of the partition. And for a given element X, denote by square brackets X the cell to which it belongs. The first theorem that we're going to prove is that for a fixed set X, we have that an equivalence relation yields a partition of the set. where the cells are like this for every x. The cell containing x is the subset of those elements that are equivalent to x. Conversely, a given partition provides an equivalence relation on x. And the rule here is that x is equivalent to y whenever they are in the same cell. So the cell containing x is the same cell that contains y. Let me first prove that an equivalence relation yields a partition. For proving one, let x be any element. We know that the equivalence relation is reflexive. Meaning that x is equivalent to itself. Therefore, x belongs to the cell defined by x. So x is in at least one cell. Now I want to show that it is in at most one cell. Assume that this x lies in the cell defined by y. Then we want to show that the cell defined by x coincides with the cell defined by y. In order to do this, I want to show that an element T lies in the left subset, if and only if it lies in the right subset. Let me do this. Let T be an element in the cell defined by x, which by definition means that x is equivalent to T, but also we know that x belongs to y, so y is equivalent to x by this assumption. Now, the equivalence relation is symmetric and transitive. So this yields that T is equivalent to y. And if T is equivalent to y, knowing that y is equivalent to x, it yields x is equivalent to T. So I write a double-sided arrow here. And t equivalent to y, it is the same as saying that y is equivalent to t, or in other words, that t lies in the equivalence class of y. So we showed that any element lies in X if and only if it lies in Y. So these two sets coincide. So X is in exactly one cell. Now let us show the converse. Assume I have a partition, and I want to show that it defines an equivalence relation. So I want to check the three axioms of an equivalence relation. So first, it is reflexive. We know that the cell containing X is equal to itself. Therefore, X is related to itself. So reflexivity holds. Let's show that this relation is symmetric. If the cell containing X is equal to the cell that contains Y, it is the same as saying the other way around. So X equivalent to Y is the same as saying that Y is equivalent to X. So this relation is also symmetric. And let's see that this relation is transitive. If X is equivalent to Y and Y is equivalent to Z, then the three cells are equal. In particular, the cell defined by X is equal to the cell defined by Z. So X is equivalent to Z. And this is a relation that satisfies all three axioms of the equivalence relation. And therefore, we proved the other direction of the theorem. This theorem yields the following definition. The cells induced by an equivalence relation are called equivalence classes. So this cell is called the equivalence class of X. And if we are given an equivalence relation, then we can define the quotient set. It is denoted by X slash tilde, and it is the set of all equivalence classes. This can also be called quotient by this equivalence relation. From this, we get a map of sets. which is called canonical projection. And I can call it pi. It goes from x to x/tilde, and it sends x to the equivalence class of x. We can observe that this map is surjective. And f of x is equal to f of y, if and only if x is equivalent to y. Let me consider some examples of taking quotient sets. In the first example, we take z and we split it into two parts, even integers and odd integers. The corresponding equivalence relation is that x is equivalent to y, if and only if, by definition, x and y have the same parity. And the quotient set will contain two equivalence classes. So it will contain the equivalence class of 0 and the equivalence class of 1. In the next lecture, we will generalize this example further, where we can divide z into more than two equivalence classes. In this example, we can say that the equivalence class of 0 is equal to 2, is equal to 4, is equal to -2, is equal to 2022, and so on. In another example, we can take x to be the set of all residents in the United States. And we can use an equivalence the equivalence relation given by age, as we talked about it before. This is called the population pyramid in 2020. And the equivalence classes are given by numbers. So here, each horizontal line gives one equivalence class. So this is an equivalence class of all residents aged 0 years. Equivalence class, I can call it x0. So this can be the equivalence class x50. All the residents that are exactly 50 years. And you can see that in the population pyramid, they distinguish, they draw males on the left side and females on the right side, but it doesn't matter for our equivalence relation, because women of aged 50 are equivalent to men aged 50. And there is one line that may contain more than one equivalence class in our definition. And this these are people 100 years and older.